Somewhere in Fort Worth, Texas, behind fences patrolled around the clock, sits a building so large that entire city blocks could disappear inside it and never be found again. 27 acres under one roof. No windows facing the outside world. No signs announcing what happens within. And yet, every single day, something is being built inside that building that most governments on Earth are desperate to understand, replicate, or simply get their hands on for a few uninterrupted minutes. This is the home of the F-35 Lightning II, and what you're about to see is the closest most people will ever get to the process that turns raw titanium, carbon fiber, and classified software into the most expensive weapons program in human history. Over $400 billion has been poured into this production line alone. Thousands of engineers, machinists, and technicians move through these halls every shift, many of them cleared to see only their own narrow piece of the puzzle, because no single person outside a select few is allowed to understand the whole machine from nose to tail. Some workstations are walled off with curtains, some tools are locked in cages between uses. Some components arrive in sealed crates from suppliers who don't know what the part becomes once it leaves their hands. This is not paranoia. This is standard procedure for a jet designed to be nearly invisible to radar, faster than sound, and networked into a battlefield picture that no other aircraft on the planet can see. Every rivet, every panel gap, every layer of coating on this jet has a purpose most of us will never fully grasp. And yet somehow, over the next few minutes, we're going to walk through exactly how it comes together, piece by piece, station by station, until a $200 million machine rolls out of a factory door and into the sky. It starts long before anything looks like an airplane. In a separate part of the facility, away from the main assembly floor, technicians work with rolls of carbon fiber material, thin as fabric, black as coal dust, and stronger than steel by weight. These sheets are cut by machines guided with a precision no human hand could match, layered one on top of another in specific orientations, then placed into massive ovens called autoclaves, pressure vessels that bake the material at carefully controlled temperatures for hours at a time. What comes out is not fabric anymore. It's a rigid composite structure, part of a wing skin or a fuselage panel, lighter than the equivalent piece of aluminum, but able to withstand forces that would crumple conventional metal. Roughly a third of this aircraft's structural weight comes from these composite materials, and the exact recipes, the layup patterns, the curing schedules are treated with the kind of secrecy usually reserved for something out of a spy film. Workers in this section often can't discuss their specific tasks even with colleagues one station over. From there, the major structural sections begin to take shape in different corners of the country before ever meeting each other. The forward fuselage, the section that will eventually house the cockpit and the nose landing gear, is built in one facility. The center fuselage, the section that carries the weapons bay and much of the internal fuel, comes from another. The aft fuselage and the tail section, where the massive single engine will eventually sit, arrive from yet another supplier, shipped across the country in oversized cargo planes and specially designed trucks that move under military escort. When these massive metal and composite shells finally arrive at the Fort Worth plant, they look nothing like a fighter jet. They look like industrial shipping containers, hollow and skeletal, waiting for the thousands of systems that will eventually fill every inch of empty space inside them. This is where the real transformation begins, on what's called the moving assembly line, one of the most closely watched sections of the entire facility. Unlike older fighter programs, where a single aircraft sat in one spot for months while workers swarmed around it, the F-35 line was designed to function more like an automobile factory. The aircraft physically moves down the line, station to station, at a slow, continuous pace, while different teams complete different stages of construction. At the first stations, workers begin mating the forward, center, and aft fuselage sections together. This is a moment of extraordinary precision. Thousands of wires, tubes, and structural fasteners must align within fractions of a millimeter because these sections were built in different states by different companies, months apart, and yet they need to come together as if they were carved from a single block. Laser-guided positioning systems help align the sections before the final structural joints are secured, a process that can take days for a single aircraft depending on how the schedule is running that week. Once the fuselage is mated into a single structure, the aircraft starts to look recognizable, though it's still an empty shell in many ways. This is when the internal systems begin their invasion of every available cavity. Miles of wiring bundles, carefully bundled and labeled, snake through channels that were designed years earlier down to the millimeter, because there is no room for error and very little room for anything at all. Hydraulic lines, fuel lines, environmental control ducting, all of it has to be threaded through spaces barely large enough for a technician's forearm. Many workers on this part of the line specialize in a single system for years, becoming experts in one narrow slice of the aircraft's nervous system, never fully seeing how their piece connects to the whole. Then comes the engine, arguably the most powerful single component ever placed inside a fighter jet fuselage, capable of pushing this aircraft well past the speed of sound and lifting it vertically off short runways and ship decks in its specialized variant. The engine itself is manufactured separately, tested extensively on its own before it ever reaches the aircraft, then carefully lowered into the aft fuselage section using an overhead crane system, a process technicians describe as somewhere between surgery and precision engineering. Once seated, it's connected to fuel systems, control systems, and the exhaust nozzle assembly that will eventually glow white-hot every time this aircraft takes flight. You imagined this was just about screwing metal parts together, didn't it? The real secret buried inside every one of these jets isn't the metal at all. It's something far less visible, and we're about to show you exactly how it's built into the skin of this aircraft. Before we go further, if this kind of restricted access footage is something you want more of, drop a comment below telling us which classified factory or hidden production line we should expose next. Hit like if this is blowing your mind so far, and subscribe if you want to keep getting access to places most people will never see with their own eyes, because what comes next is the part they really don't want getting out. With the internal systems installed and the engine secured, the aircraft moves toward one of the most secretive stages in the entire process, the application of its radar-absorbing coatings. This is the layer that gives the F-35 its reduced radar signature, and unlike the older stealth aircraft of decades past, this coating isn't simply painted on as an afterthought. It's engineered into the structure itself, applied in specialized booths where environmental conditions, temperature, humidity, and airflow are monitored constantly. Technicians in full protective gear apply these materials in careful layered passes, and the exact composition of these coatings remains one of the most closely guarded secrets in the entire program. Even small imperfections, a slightly uneven seam, a gap around a panel fastener can affect how the aircraft appears on enemy radar. So every surface is inspected repeatedly under specific lighting conditions designed to reveal flaws invisible to the naked eye in normal light. Once the coatings are cured and inspected, the aircraft rolls toward avionics integration, where the true brain of the machine comes online for the first time. Miles of fiber optic and copper wiring connect to processors and sensor arrays embedded throughout the airframe. From the distributed aperture system, sensors positioned around the fuselage that give pilots a 360-degree view of the battle space, to the radar systems housed in the nose section. Technicians power up sections of the aircraft systems in stages, running diagnostic checks that can take days, searching for any fault in a network so complex that a single aircraft contains more lines of software code than entire previous generations of fighter jets combined. This is the stage where the jet transforms from an empty metal and composite shell into something that can actually think, sense, and communicate with other aircraft, ships, and ground stations across a secure data network that most of the public will never fully understand. Did you imagine this process was mostly mechanical? The truth is, this aircraft spends nearly as much time being coded and calibrated as it does being physically built. Every sensor has to be aligned. Every software subsystem has to be checked against thousands of test parameters. Technicians run through checklists that stretch for pages, verifying that weapons bay doors open and close within precise timing tolerances, that the ejection seat systems are wired correctly, that every warning light in the cockpit responds exactly as designed under simulated failure conditions. As the aircraft nears the end of the moving line, it enters what workers sometimes call the final finish stations, where exterior panels are fitted with the precision of custom furniture making. Cockpit displays are installed and tested under different lighting conditions to simulate day and night operations, and the landing gear, capable of absorbing the violent impact of both conventional runway landings and, in certain variants, vertical landings on ship decks, is installed and cycled repeatedly to confirm it operates flawlessly. Every one of these final touches is documented, photographed, and logged into a digital record that follows this specific aircraft for its entire operational life, sometimes 20 years or more of service. Before this jet ever carries a pilot into the sky, it undergoes a process that surprises most people who assume a fighter jet simply rolls off a line ready to fly. Fuel systems are filled and checked for leaks under pressure. Engines are started on the ground and run through extensive checks while the aircraft remains anchored in place. Technicians monitoring every gauge for the slightest deviation from expected performance. Only after passing dozens of these ground tests does the aircraft move to the flight line for its first actual flight, still officially considered part of the manufacturing and acceptance process rather than operational service. Test pilots, often former military aviators with specialized certifications, take the aircraft through a series of increasingly demanding maneuvers, checking flight control responsiveness, engine performance at different altitudes, and sensor accuracy against known reference points on the ground. What most people never see is what happens if something doesn't check out perfectly. An aircraft can be sent back through specific stations for rework, sometimes over relatively minor issues that most passengers on a commercial flight would never even notice, because the tolerance for error in a machine designed for combat operations is measured in standards far stricter than almost any other manufactured object on Earth. Every one of these jets that eventually gets delivered to a squadron, whether in the United States or one of the partner nations involved in the program, has passed through this entire gauntlet, station by station, inspection by inspection, until it finally earns the right to wear its assigned squadron markings and fly its first operational mission. So now you've seen what most people never will: the hidden stages, the sealed rooms, the coatings applied in near silence, the software checks that stretch on for days, the final tests that determine whether $200 million of engineering becomes a functioning weapon or gets sent back down the line for another round of scrutiny. What part of this process surprised you the most? Was it the coatings, the software, or the sheer scale of secrecy involved in getting one aircraft from a roll of carbon fiber to a fighter jet capable of operating in the most contested airspace on the planet? Let us know in the comments, and if you want to see what happens inside the next restricted facility we managed to get access to, make sure you're subscribed, because there's a lot more hidden in plain sight than most people ever realize.